Well, welcome everybody. Thank you, Dan, for that fantastic introduction. Yes, I do keep myself busy, it's true. But it's real pleasure to be here tonight. So it's a real pleasure to be here in this famous lecture theatre in a well-known and famous city of London, okay? I also live in the city of Bristol, and I'm here to talk about cities today. So it's really important that we discuss cities. A third of the world's population live in cities today, and by 2050, that will go up to about 50% or even more. It's really important that we make cities more livable and greener and more healthy. So, as you can see, I've put a lovely picture of my home city, Bristol, on the screen here. This is a picture of the harbour. It makes it look really nice and calm here. It doesn't reveal how many hills there are in Bristol. It's a very hilly city. And this also makes it look like a very calm city. But actually, Bristol is a real, lively, vibrant, messy city. And I really want to talk about real messy cities that we live in today. So Bristol is famous for its street art, including lots of Banksy. Its activism also reflected in its street art, and we even have our own republic. This is a street in Bristol called Stokes Croft, and somebody said at the People's Republic of Stokes Croft, we've even got something called the Bristol Pound. Okay, I want to talk about real cities and the real people living in them, and how technology can help real people. Okay, and what I'm going to talk about is technology in cities. And in fact, I'm talking about the smart city, this idea of a smart city. So what is that? Well, what a smart city is a city that is consuming huge amounts of data to dynamically run the city in a more efficient way. This could be data from sensors put around the city. It could be smart meters in buildings and homes, or it might be even your smartphones or your wearable technology. Okay, some examples of what it can do are things like smart traffic balancing. So instead of having the traffic lights just set so that they're constantly on the same cycle, a smart city will monitor the traffic and control the flow of traffic around the city in a more dynamic way. So it might be controlling how the traffic moves. If you've got a big event, for example, and more traffic than you expect, or it might be ensuring that emergency vehicles actually get through. We've also, a smart city is also looking at how energy is consumed in a more dynamic way in a city. So we've got a big challenge coming up as we go towards net zero, more solar panels on roofs, even things like vertical wind turbines. And this is a more complicated, dynamic way of how energy is generated and managed. So smart meters are going to be looking at how we consume energy in a more granular way and controlling how that energy is moved around the city to ensure that we're making the best use of it. For example, cooling down refrigerators in supermarkets overnight when there's less energy, for example, this kind of thing. Now, this vision of a smart city that's using a lot of data almost looks like the ideal future, like a utopian future, so green and calm and peaceful and so on. And there are even visions of cities for the future to be built from scratch. Okay, so this is a really unusual city. I think this is the most extreme city that I've seen that's planned. This is called The Line, and it's being built by a company called NEOM in the desert in Saudi Arabia. So this is a really unusual city. So this city is 170 kilometers long, or it will be once it's finished, but only about 500 meters wide and 500 meters tall. So people will live in this city in sort of 3D blocks. There's no cars. You have a high-speed railway down the whole of the line. And the whole thing is climate controlled, and things like the food being brought in and energy and everything is completely controlled, even by things like data from people's phones and things like facial recognition. Now, you might hear that and think, I'm not really sure that's what I want. Do we all want facial recognition? All this data about us being given to whoever's running this place? Who's going to be running it? Could be the government, could be some big tech firms. And actually, this is a really big issue with smart cities and this kind of technology. Who gets to control that data? How can I contribute to a smart city but keep my privacy and so on? And is this really safe? I mean, isn't this reliance on all this technology and all the communication between these systems really vulnerable to cyber attacks as well? So that's something I'm going to talk about in the second part of my talk. But I'm going to go back now and go away from this utopian or possibly dystopian vision of a future city and come a bit more down to earth. In fact, I'm going to really go down to earth by discussing the city underground. So this is a front page of a rail accident report of an accident that happened in 2013. So what happened here, this is a railway tunnel, National Railway Tunnel in London, so going through the centre of London, about 15 metres below the ground. And there were reports of this huge drill bit just found on the line, okay? Very lucky that it didn't cause a derailment and a really nasty accident. So what happened here was that somebody above the ground was building a big apartment block, wanted to drill piles into that ground, okay, to secure it. And they thought they had checked everything, the utilities, they checked the underground map, but they hadn't checked the national rail map, okay? So this obviously is, this caused a huge amount of disruption, of course, but really this is all human error. But the real reason that this happened was, of course, there are no, you'll be really surprised to find there really are no decent maps of what's going on underground in London. We don't know where our utilities are. We don't know necessarily where all the cables are. And even if there is a map like this, it doesn't necessarily have the 3D detail. And, it might be a scanned PDF somewhere online, and not a particularly useful thing. But that's actually a really big problem, because as this diagram shows, the underground of a city is as complex and varied as the above ground of a city. It's like a sort of second city in itself. So you've got things like, just below the surface, you've got things like water and sewage works, you've got electricity supplies, gas, you've got telecommunications cables, and then you've got things like various trains running through it as well. And even things like the water table change. You've even got weather underground, okay? So this is a really complex system. And we don't really have decent maps of these things. It's a really big problem. So to find out where things are, often what you do is you just have to dig a hole in the road. And you know how much disruption that causes with all the traffic and so on. Also, when people are digging up the road, it's very often they just hit a utility because they don't know where it is there. They'll hit a cable or something. In fact, there's about 60,000 instances of this happening throughout the UK, and it costs the UK about £2.4 billion. So solving this problem of not knowing where everything is in the ground is a really huge problem. So how are we going to solve them? Why am I, as a quantum physicist, here talking about what's going on underground and pipes and things? Well, enter this strange device here. So this is from the University of Birmingham, and it's a result of something called the UK Quantum Technology Hub Sensors on Sensors and Timing. So what you've got here is a big black box full of some electronics, but the real business end is this big tube here. Okay, and what this tube is it's got a vacuum inside, and inside what you do is you drop a bunch of atoms and watch it fall, and then you measure how quickly those fall, and it allows you to measure the strength of the gravity, okay, the acceleration due to gravity, which we often call g, okay. So why would you do that? Well, it turns out that the acceleration due to gravity, you may have done this in your science classes long ago, is not actually constant like we think it is. There are tiny variations in the force due to gravity. If you look in the bottom corner there, you can see that the whole globe actually sees small variations in acceleration due to gravity. They're very small, so between sort of a billionth of the Earth's gravitational field and a trillionth. But really, you're talking about changes that you can still pick up. For example, mineral deposits will change the density, and therefore that will change the gravitational field strength. Or a big hole underground, like a tunnel, that's going to cause a change in density, and that can be picked up as well. Even things like buildings, okay? And the device that Birmingham have made, I showed on the last slide, is able to sense things like tunnels, even down to about 10 meters below the ground, and mineral deposits and buildings. And in fact, is not very far away from being able to detect the gravitational field strength of a person. So we're really getting to the point where these are incredibly sensitive. We could tell that a person's there by measuring their gravitational field strength. So really incredibly sensitive. Now, why is dropping a bunch of atoms more sensitive than any other technique? Let's say dropping a tennis ball. They're both made of mass, should make no difference. Well, one reason is the fact that compared to other what we call gravimeters, is dropping atoms through a vacuum, okay? So it's very insensitive to any vibrations. So normal gravimeters are basically based on the mass on a spring, but that spring will pick up vibrations. And even if you live in a place without much seismic activity, there's always small earth tremors, and there's always things like traffic causing vibrations. So that causes a lot of noise on your data. But dropping it through a vacuum means that you measure it before it hits the lower surface, and then you never actually pick up any of those vibrations. And that's one reason, but the other reason is actually it's going to take a little bit more explaining, going away from this sort of down-to-earth stuff and going all the way into the physics of single particles. Okay, now this image here is all about what fundamental particles really are. So this is a picture that you can make if you thin down a very, very narrow piece of metal down to the point where you get a few atoms on the tip, and you scan the surface, okay? And with that, you can pick up atoms, and what you see in that ring there is a whole load of atoms being picked up and put into what we call a corral, okay, that circle. What we then do is put an electron into the middle. So electron's one of the fundamental particles, okay? So what we see there, what look like ripples in the center. And those ripples come about because an electron behaves like a wave. We know it's a particle, but it also behaves like a wave. And other things behave like waves as well, including light. Light is made of photons, but it also behaves like a wave. And the first person to actually prove that was a guy called Thomas Young. He actually did lectures here in this theatre, I believe, showing that light behaves like a wave. And I'm going to show you how that works now. So this is a green laser. I'm going to put this one on. And what you see here, if I can get that to, there we are. Josh, can we lower the lights? That's perfect. Good. Okay, you can see here the laser spot. Now, what I'm going to do is move this thing here with a small slit in it, okay? I'll move this across, and you should see, be careful, do you see this stripe across here with bright and dark pattern, okay? Why do we have that pattern? Well, what's happening here is that the light goes either side of this slit, and it takes an infinitesimally different path length to a place on the screen, okay? If the path difference means that the two waves, when they meet, are in sync, so the peaks and the troughs are coming at exactly the same time, that's something called constructive interference, and we get a bright spot. But if the peaks and the troughs are out of sync, then that gives us destructive interference, and we get a dark spot. And you see this succession of bright and dark here. Okay, this is incontrovertible proof that light is a wave, okay? This was really a part of huge debate at the time. Newton said that light is a particle and everyone believed him until Young proved him wrong, okay? The other really fascinating thing here is that you can actually see the effect of this wave over a length scale. You can really see this is a good, almost a centimetre here. But the wavelength of this light, you can actually, if you do use some simple sums, you can work out exactly what that wavelength of light is, okay? And this green light is about 500 nanometers. Now, a nanometer is a billionth of a meter, okay, or a millionth of a millimeter. So really, really tiny. But using this technique, we can actually see that pattern. I also want you to point out to you that if I just tap this, oh, no, this one, sorry. Oh, there we go. You can see that it moves about. It's actually very, very sensitive to the position of this slit here, okay? So actually, this is a very good way to measure movement as well. Josh, can we have the lights up again? That's great. Okay, and it's that, and this is sort of the wave phenomenon that we're going to use. Now, we know that basically all matter pretty much is made up of fundamental particles. You chop up material smaller and smaller and smaller, and then you get to the point where you can't chop it up anymore, and that's when you get to fundamental particles. So, for example, a photon, we'll talk about how photons can be waves a little bit later, but a photon is a single particle of light. An electron is a single particle as well, that goes around the outside of an atom. The center are protons and neutrons. These are all fundamental particles, okay? And actually, this guy here, this picture here is somebody called Louis de Broglie. He is a Belgian physicist, and he made a hypothesis that every fundamental particle has a wave-like nature as well. And in fact, you can work out its wavelength, the distance between the two peaks, okay? And the wavelength depends on both the mass and the temperature. And temperature is actually how the molecules are within something are moving, how fast they're moving. So you can see this is why we don't have a wavelength, or we have a wavelength, we never see it, okay? So the wavelength of us is incredibly, incredibly tiny because we're very massive and we're very hot, okay? If you work it out, our wavelength is many, many, many times smaller than even the width of the nucleus of an atom. So we're never going to see that. So if you want to see the wavelength of a particle, you need to go to very small things and very cold things. Okay. And to understand what we mean by cold, we can have a look at this scale here. So as I said, temperature is actually given by how much individual particles are vibrating, okay? The more they vibrate, the warmer the temperature. It means more energy, okay? And physicists have come up with a way of describing that. We don't talk about temperature usually in terms of Celsius. We talk about a different scale called the Kelvin scale. And the Kelvin scale says that we start 0 when everything stops moving, and that we call absolute zero. It's actually impossible to get to absolute zero because you never really can get everything to really stop moving. But what we can do is go closer and closer and closer and closer. And this scale of this thermometer here shows that we really need to step. This one shows a decrease of 10 times for every single step. Okay, so the room here is about 300 Kelvin, okay? 300, 320 Kelvin or thereabouts, okay? And, that's when, roughly sort of when ice sort of begins to melt and things like that. If we want to go a bit cooler, well, we can begin to freeze the air, actually, or cool down the air, and we'll begin to see that the individual components begin to turn into liquid. So liquid nitrogen, for example, is a liquid at 77 Kelvin. Really quite cold, okay? And the lightest gas of all, helium, becomes liquid at 4 degrees Kelvin, okay? We often use helium as a cryogenic coolant because it reaches 4 Kelvin. You can also use hydrogen. It's also about the same temperature, but hydrogen is kind of explosive. And liquid, helium is much safer because it's an inert gas. So much better to use helium than hydrogen. And even things like the universe has a temperature. So the universe has expanded since the Big Bang, and it turns out there's residual energy within the universe that gives it a temperature of about 3 degrees Kelvin. Okay, but what we're going to do is go much, much lower than that. So if you look at the left here, you can see that when we have hot gas, the molecules are moving around very fast, and we can work out using that equation that I showed you before that the wavelength is really short. We're talking about 10 picometers, and a picometer is a millionth of a meter, so really tiny. You're not going to see that. And as you cool it down, you start to see the wave-like properties. But as you really, really, really cool it down, and we're talking to 100 nanokelvin, okay? 100 nanokelvin is 100 billionths of a degree above absolute zero. So this is really about as cold as we can make anything. The waves and atoms really spread out, okay? Now we see waves of about 600 nanometers, and that's more or less the same wavelength as this green light here. What happens then is that as the waves expand, they overlap and they begin to interact with each other. And it was discovered by a guy called Bose, who wrote a letter to Einstein, who said, I think you get a new state of matter if this happens, okay? And he said all the waves will act in sync, okay? They all have the same phase and the same wavelength altogether, act like one big super atom, okay? And it was many, many years after Bose and Einstein wrote about this that this was actually proven. But in the sort of 80s, the Bose-Einstein condensate was actually made. Okay, but actually that's what we're using in this gravimeter. So a gravimeter actually makes clouds of atoms in the Bose-Einstein condensate. Okay, now in this gravimeter, what you do is you actually make 2 of these clouds and you throw them up into the air, inside this evacuated chamber, and let them fall down again, okay? And as they fall down, at some point they'll overlap, okay? But these are 2 almost like big super atoms which behave like waves. So you're going to see a sort of interference pattern, just like we see here. And you can look at where the peaks and troughs are of that interference pattern and get a lot of information about how fast that's been going. So you can see the change in the interference patterns and the change in the spacing there. And it's an incredibly accurate way to measure tiny changes in velocity and therefore the acceleration due to gravity. Okay. So the accuracy of this is incredibly tiny. So you're talking sort of a billionth or a trillionth of the gravity due to the Earth's magnetic field. But what you can also do with these kind of atoms is use them to very, very precisely measure movement. So in your phone, you'll have something called an accelerometer, which is measuring when you change the speed of your phone or the direction. So you need an accelerometer. You also have a gyroscope in there, okay? But they're not particularly accurate. Atoms, when they do this in this Bose-Einstein condensate, are much more accurate. So you can use these for navigation. To know your position, you need to know where you started, and then how fast you've been going, and whether you've undergone any rotation. And you also need to know the time very accurately. So actually, you might need an atomic clock to do this as well. But that will allow you to plot your position as you go, okay? Now, this is something called navigation by dead reckoning, okay? And that's not how navigation happens with your phone today, okay? Your phone is using GPS. So basically what it's doing is it's got a sight to the sky, and 3 satellites are triangulating the position of your phone, okay? Now, that's not particularly accurate, and there's a big problem if you don't have sight of these satellites, or if you're indoors or you're underground, okay? So having a navigation system that doesn't use GPS is really, really helpful. In fact, you can always use these dead reckoning systems and combine them with gravity maps and magnetic field maps. So we also get the same effect with magnetic fields. You get tiny changes in magnetic field that you can map out as well. So you get a big combination of all these quantum sensor technology to determine position. Okay, why would you want to look indoors and underground? Well, just think about the move towards autonomous vehicles and autonomous delivery systems, for example. You want to be sure that a vehicle navigating is able to find its position and make sure that's incredibly reliable. It can't just have a fallout of the GPS. It might not be so important for a little kind of, sort of Amazon delivery robot, but if you're in a car, you want to be absolutely sure where all of your cars are with very, very high accuracy. And if you go underground in a tunnel, for example, then you really don't want to lose that position. Okay, so if you're working towards an autonomous vehicle city, this kind of navigation system is really important. You also want to navigate underground, okay? This might be, in underground stations. It's obvious in the tube how useful that would be. But also in large buildings, let's say a hospital. You know how complex hospitals are. Everybody gets lost in hospitals. Wouldn't it be great to have an indoor map and a phone telling you where you are within the hospital? Okay, that would put a lot of patients at ease. It would also allow small deliveries autonomously between, to take test samples to the lab, for example. And just think how great it would be to have, when you're in a big shopping centre, to be able to just find the shop that you want and to kind of get a route to that as well. So you can see that there's also, commercial reasons why you might want this. So that's why there's this idea of a sort of quantum compass. And this is a picture of a prototype quantum compass put together by in Imperial College London. So you can see that this is quite a complex contraption. They put it into a big white box, and they have put this on the underground, okay? So this is on the tube, and it actually works pretty well. But of course, it's not yet pocket-sized, okay? So this isn't, I don't think in rush hour you're going to be wheeling this around to help you. I'm not sure how you're going to get it up and down the escalators either. Okay, so can you make these smaller? Well, there is progress towards that. So this is an atomic chip, okay? This is much, much smaller. So what we have here is little wires, and the little wires generate little magnetic fields that trap electrons, okay? And they trap electrons, and they keep the atom. They keep the atoms hovering above these wires, okay? So this is, a much smaller device, small, sort of pocket-sized. These aren't quite as accurate as those big systems yet, okay? But really, this is quite a new technology, and I think what I've seen is that how rapidly these kind of systems are shrinking down, becoming smaller, consuming less energy, so you need less battery power for them. It's really happening very, very quickly. Okay, I still think we're quite far away from really having, handheld, portable quantum navigation systems, but I don't think it's very far off. You can certainly put them on ships, and you can put them on airplanes already. Okay, so we've talked about navigation and underground, and actually the idea of autonomous vehicles is a really quite attractive one if we want to have a more livable, greener city. You could imagine freeing up a lot of space in the city if you had autonomous vehicle transport. This is a artist visualization of what Oxford Street would look like if it was pedestrianised. Okay, so you can see it looks quite nice and green. And I think a lot of this technology that we're looking at is about making our city spaces more pleasant to live in. Okay, but I want to come back to this idea of this city using all this data. Okay, and this data is all about us. Okay, we want to be sure that we can contribute to this smart city, but without actually giving all our personal information away. We want some control over that. We also want to be able to take part in sort of democratic processes in the city in a more active way. Again, without but being able to sort of have anonymous voting. And also, we're thinking about the reliability of all these systems. Well, we want to make sure that we're not vulnerable to cyber attacks as well. And that's what I want to talk about in this next part. So, in particular, the infrastructure that we use is some of this is what we call critical infrastructure. So this is the things that we really need when it comes to keeping a city like this functioning, okay? This means making sure the lights stay on when we have energy, making sure that healthcare systems keep going, water's available, communications available, that people can get around and deliver food and groceries. And even it's really important to keep banking and finance going. If you can't pay people or pay for deliveries, then you're really in trouble, okay? Now, it's important that any communication with these systems is incredibly secure and it's not vulnerable to hackers, okay? Cybersecurity attacks, attempts at those are being made all the time. So it's really, really important as we become more and more dependent on these systems that they're really, really secure and they're not hackable. Okay, so cybersecurity of data is really important, but it's actually a very old topic, okay? Cryptography is something that goes back thousands of years. And in fact, there's a very reliable system to ensure that we send data in a very secure way, and it's called the one-time pad. Now, what a one-time pad used to be was 2 booklets of paper with random numbers on them, to the same random numbers, okay? And the sender and the receiver would have 1 copy each, okay? So what you would do is you would take your message, encode it into binary, that's called your plain text, and then you sort of multiply it by one of these random numbers, okay? And you must importantly, when you've used that random number, you cross it out and don't use it again, because then somebody could hack it. But when you do that, you get something called the ciphertext, and that ciphertext is unhackable. So the way this is done in this particular one is by comparing the plain text and the secret key and making it a 1 if they're different and a 0 if they're the same, okay? And that makes it a completely random process. There's no way from the ciphertext that you can tell what the plain text was as long as that secret key is completely random, okay? You need the secret key to be able to decrypt it. But of course, this is not really something that's useful for the internet age, is it? We can't give each other, everybody that we interact with, a little booklet, okay? And when we talk about sending data, we're talking about many gigabits per second, so that's many billions of bits per second in normal telecommunications, okay? So this isn't going to cut it. Okay, so we need to think more carefully about how we do cybersecurity over telecom systems. So I'm going to introduce you to some characters in cybersecurity. So the sender in cybersecurity is always starts with A, called Alice, okay? And Alice is in love with a guy called Bob, okay? Alice and Bob are always the sender and receiver in cryptography. And in our case, Alice is sending Bob a signal using light, okay? Little pulses of light. And we'll talk about how they send it across the channel in a minute. Now, in cryptography speak, there's always an eavesdropper. You always have to assume there's an eavesdropper. And the eavesdropper is called Eve, okay? So you'll see very serious science papers talking about Alice and Bob and Eve getting, trying to kind of eavesdrop on the messages, okay? So Alice is trying to send Bob a message, but she's sending it using light, okay? Now, you might think that, that means that Alice needs to have a sort of clear sight to Bob because light, as we know, travels in straight lines, okay? I can demonstrate that. So here we have a laser pointer. If I can get this to work, here we are. I'm just pointing it to just away from the cameraman there. Whoop. Sorry, this is a little bit of adjustment. There we go. Okay, can we have the lights down, please, Josh? There we are, that's a bit better. Okay, can you see? Oop. No, because it's turned off. Oop. Here we are. Oop. There, you can see that laser, can't you? Okay. Yes, there we go. See, that's going in a straight line, isn't it? Okay. Right. But I can make it go around corners. Josh, I think I'll need the lights up again for this. Now I'm going to turn this round. This is a bucket full of water. Okay. And if I just adjust it slightly, put it through there. This little bit of alignment. There. Oh. There. Okay, what I'm going to do here is open this into a stream of water. Let's hope this goes in the right place. Oh, no, almost, there we are. Now, can we have the lights down again, please? Josh, there we go. There we are. Now, do you see the light isn't going straight forward anymore, it's going down through this beam of water. Now, why is that? Well, what happens here is that the light travels more slowly inside the water. This is because it has something called a refractive index, but essentially means the light is going slower. So what happens is that it bounces back and forth between the surface of the water where it hits the air, and it can't go fast enough to go outside into the air, so it has to stay in the water in a process called total internal reflection. Okay, and it's bouncing through here, and actually you can see it's going all the way in here. You can see the light coming down here. It's a really nice demonstration. I'll put it there. Okay, now if I find my laser pointer for a start, how does that? We can't send light signals through water. That wouldn't be particularly practical. So I think I'll turn that one off now. Now, this is a bit more like how we're going to send a signal from Alice to Bob. Okay, this is a Perspex pipe, and we're going to make this light really go around a corner. So I'm going to shine the light in here. Now, do you see where it's reflecting from the surface there? Okay, and you can see as it comes out, there's a really nice bright light coming on the surface there. Okay, so you can see it bouncing around. There. Have the lights on again? Perfect. Now, what we saw there, there we are, was you saw the path going through, okay? Now, if we're sending a light signal from Alice to Bob, this will be okay over this short pipe. But the actual fact that you can see that light path is because every time you hit a little bubble or a little defect within this, with this pipe here, it scatters towards you, okay? Now, that means that the energy in that laser beam is being lost, okay? This is okay for this sort of 1.5 meters that we're going through here, but that isn't actually what we want if we're sending signals over very long distances. So it's a phenomenal development of technology to be able to send light down very long distances. We have these things called optical fibers. I'm sure you've heard of these, which are basically made of glass, which is actually flexible. And it's just, the width of about a human hair, okay? But it took a long time to really get the ability to be able to send over several tens or hundreds of kilometers using these optical fibers. And in fact, it was the hard work of a scientist called Charles Cow, who was really working at the science of glass and how to remove defects and look at how to actually, what we call pull optical fibers to make them absolutely pure, okay? And so now we can signal over 100 kilometers down an optical fiber. So it's like having a block of glass and being able to look through that block of glass for 100 kilometers and still being able to see out the other end. It's really an extraordinary technology. And that's why he won the 2009 Nobel Prize, very deservedly. But actually, this work was done very close to here, so it's just sort of north of London. So this work was done in Harlow at the Standard Telecommunications Laboratories in the 60s. So it's actually a British invention as well. Okay, so we're sending signal down these optical fibers, and we can send pulses, but we need to encode the information in ones and zeros. So how are we going to do that? Well, we use something called polarization. And polarization is exploiting the wave-like properties of light and saying that when something's waving, it's got to wave in a particular direction. So light might be waving along the horizontal plane, or it might be waving along the vertical plane, okay? I'm going to encode a 0 in the horizontal plane and a 1 in the vertical plane, okay? And I have this VH kind of, what I call a basis here. Now, what I can do is just rotate that by 45 degrees and encode in a diagonal basis and one at 90 degrees, which I call an anti-diagonal basis, okay? Now, I can use whichever one I like. but I've got to know what basis I'm using. If I try to use a kind of an AD filter to measure a vertical polarized photon, half the light will go into the A one and half of the light will go into the D one. So I don't know whether I've got a 0 or a 1. And it's important to understand that you need to get these bases right. So Alice is sending pulses of light with either vertical or horizontal polarization to Bob. And Eve wants to measure that signal. What's Eve going to do? She's going to get a little device called a splitter. Okay, and a splitter basically takes a tiny amount of that light away from the main beam. Bob may notice a small reduction in intensity, but he's going to expect that because there will be some loss over a fiber. And what Eve is going to do is split that light into 4 and measure 4 polarizations. You can measure the horizontal, vertical, diagonal, and anti-diagonal. And if she does those 4 measurements and measures how much intensity she gets in each, she can reconstruct the polarization that Alice has sent and get the code. She can even send the light back to Bob. Okay. What we really like to be able to do is have Alice be able to send information in the way that Eve can't do those 4 measurements. Now, one way to do that is to not use bright pulses of light, but to send light as single photons, okay? So if you send light as single photons, then Eve is only able to detect 1 photon at a time, okay? That means she can't do 4 measurements and determine what the polarization is. But of course, we've said that yes, light is a particle, light is a wave, but how can a particle have a polarization? And that's what we can discuss next. So we saw before, as we see here, this pattern due to interference here. Okay, interference, as I said, is a very well-known, well-characterized phenomenon in light optics. Okay, and it essentially crucially involves the fact that the light takes 2 different paths. Okay, it must take 2 different paths to be able to see this pattern on the screen here. Okay, so if I turn down the intensity of this light, so from bright light to just I'm getting 1 photon at a time, and I can do that by working out how much intensity a single photon is, then I can send single photons through the slits at one time. The question is, what happens? So if it behaves like a particle, what you'd expect it would choose, basically it's either going to go through one slit or the other, but you won't see an interference pattern because you need 2 different paths to be able to see that. It needs to go through 2 slits at the same time. But if that particle photon is fundamentally a wave, then it will go through the 2 slits at once, and you'll see a very, very weak pattern on the screen. So let's see what happens. Let's actually, do this experiment, or at least simulate this experiment with real results. So let's send in the sort of first few photons and look at the screen. What we see on the screen are these dots, and these dots don't have any kind of wave-like pattern. They look like photons. So it looks like particle theory is winning. Let's get some more data. Looks pretty random to me. Doesn't look like I'm seeing a pattern. Even more data, I don't really see much of a pattern. But now, all of a sudden, what do we see? We see some stripes. And those stripes correspond exactly to what you'd expect to see if you had bright light and exactly where the bright parts of the interference are. So why are we seeing this pattern arising when we take the statistics of many of these photons? Well, this was a huge subject of debate in the early 20th century amongst the quantum physicists as they were emerging. Okay, and there are different interpretations of quantum physics, but the one that we generally tend to use is called the Copenhagen interpretation. And the Copenhagen interpretation, which explains all the results that we see, says that the correct way to describe the wave is not a wave of just intensity, it's a wave of probability. So you've got a wave of probability, and as that probability wave goes through the slits, it interferes and changes the probability of where the particles will hit the screen, okay? So what happens is that as as the photon moves through, it moves through as a wave of probability and generates this interference pattern. But we don't see that pattern immediately, because then what happens is the universe says, and for reasons we don't know why, that you don't see this wave pattern. The wave function part collapses, it disappears, and the universe makes a choice at that point randomly where it's going to go. Okay, it's going to obey statistical laws, so it's going to be more likely in the bright part than the dark part, but you can't predict where that photon is going to appear. It's only when you do many, many measurements and you generate the statistics that you can build up what the probability wave pattern is on that screen. So that's really quite a surprising aspect of physics, okay? It's something where, you just have to do the experiment to find out what happens. You can't predict this. You can't understand it, okay? You can't reason this. This is just the way the world is. Really, takes people quite a long time to kind of get their head around this. To be honest, I read about this when I was a teenager, and I was so fascinated that made me want to do physics. That's why I'm here, basically. So really, this is one of my favourite results of all time, this one. But what does it mean? It means that in a fundamental form, when we have single particle events, they're not predictable. We can never predict where that photon's going to go. But they do obey statistical probabilities, and that's why our macroscopic world is predictable, because we have many, many, many millions of events, usually. Okay? So that's why we have to go down to a single particle level to see what happens, and why it isn't intuitive for us in our everyday world. But if we go back to Alice and Bob now, because we want to use this wave particle duality. So Alice is now going to send a signal as single photons, okay? She's sending those to Bob one by one. And because this is still a wave, it's still got a polarization, so we can still encode in polarization. And Eve is still going to try to get a few of those photons and measure them, and she's going to analyze them. But of course now, she can only measure one photon. And let's say she gets a click on her V detector. Now, it could have been that Alice really did send a V. Or it could be that she used a different basis and she used this DA basis, in which case there's some probability that it still arrives on V, okay? So she can't accurately measure everything about that photon with just one measurement. And in fact, there's a theorem called the no-cloning theorem, which says you can never determine the state of a single quantum particle because you can never measure everything with one measurement, okay? And we're going to use that, okay? So Alice is sending Bob information, the ones and zeros, but she's changing the basis all the time randomly. And Bob, when he's detecting, is also changing the basis. He doesn't know what basis Alice is using. He collects the data, and then Alice and Bob phone each other up and just say what basis they've been using. That doesn't reveal the key in itself. It just tells you what basis you're using, and Alice and Bob then just keep the numbers they got when they had the same basis. Now, they're not going to tell Eve what those numbers were, and Eve couldn't have measured them, so she's never going to know that. If she tried to pretend to be Alice and send them to Bob, Bob would immediately see that he's not getting the numbers in the right basis. Okay, so he'll know that somebody has tried to eavesdrop on that signal. Okay, so this is something called quantum key distribution because he's sending a cryptographic key that's basically like a single photon version of a one-time pad. Okay, and the advantage of this is that you're sending information whose kind of safety is guaranteed by the laws of physics, because we know that you can't measure multiple properties of a single photon. Now, we've done this kind of quantum key distribution at Bristol. So this is a map of Bristol. You probably don't know Bristol very well, so I'll point out a few things. So at the top here in purple is our physics building. That's at the top of a hill, which is good. So that's called the Nanoscience and Quantum Information Lab. And then we send signal using an optical fiber down to an engineering one, which is the pink one called HPN Lab. And we also send signal to our Quantum Technology Innovation Centre and to our science museum called We the Curious, okay? The reason we can do that is because we have a experimental, what we call a dark fibre network in the University of Bristol, which is being used by the Telecoms Research Group. So that's really useful. That basically means we're not sending commercial internet traffic over, and it's not full of signals, so we can do really, interesting, clever experiments with it. Okay. So inside one of these nodes, it kind of looks a bit like this. Okay. You've got lots and lots of optical fibers. That's the yellow things, and polarization manipulators. That's those black things. But why have we got so many? Well, it's because we haven't just got Alice and Bob now. We've got Alice, Bob, Chloe, Dave, Feng, Gopi, Heidi, and Ivan. We've now moved away from just sending messages from a single point to a point, having a network now. Okay. Now, the way this is done is by distributing single photons, but we're now distributing 8 different colors. Everyone gets 8 different colors of photons, okay? Now, if, say, Feng and Gopi want to set up a one-time pad between them via quantum key distribution, they choose to measure a specific combination of colors, and every pair has their own combination of colors, okay? So that enables communication across the whole network, and it means we can actually make a real network where things expand. But the other important thing to note about this is that in the center with this big Greek letter phi, that's for phi for photon usually, we're generating photons as a resource and sending them out, but whoever's sending them out does not know what's being received. So actually that source there could be Eve. She's the one sending the photon, but nevertheless she doesn't know what the answers are. It's only when those pairs begin to measure those photons that they know what they were. And actually, that's really useful because it means that the end users can guarantee that nobody is able to view their communications, okay? You can change this way of doing things ever so slightly and do something called an anonymous voting protocol, where somebody can send out information without revealing who they are, okay? And that's because there's sort of different photons at each point, okay? But that's very useful for our smart city. Of course, if you have anonymous voting, you can have things like more engagement in local things and have voting at a local level and improve the democracy of a city. But it also means you can send all sorts of different information about yourself without revealing who you are. And that could be really useful. So let's imagine, say, you've got a Fitbit and the city would really like to know, what's your heart rate as you're going through different parts of the city, okay? Is it lower when you're going through the green spaces? Is it really high when you're on the tube? Are there places where people are more stressed than others? This would be really useful statistical information, but most people wouldn't really be happy to give that information freely, okay? But using this, you can actually give that data anonymously for statistical purposes without revealing who you are. So this is a way of securing your personal information. It's also a way of securing those critical links between that critical infrastructure, say between power stations and users as well, so or between hospitals and banks and things like that. So in London they're doing this. This is actually the first commercial quantum key distribution network. This is set up by BT and Toshiba in collaboration with Amazon Web Services. And on this network are the users EY and HSBC. So HSBC is a bank, of course, and banks are very interested in this kind of technology because it means that they can guarantee the security of data of both of their financial transactions and of their customers as well. So you can really see that this could be the future. So the final part of my talk, I'm just going to be talking a little bit about my research. We've looked at some research from Birmingham, from Imperial College London, and we've also seen some research from my colleagues. What I work on, as Dan said in the introduction, is semiconductors. Semiconductors are kind of material that we use. So I'm going to talk about how we can make better single photons. So you might think it's easy to make those single photons. You might get a light bulb like this, an incandescent light bulb. turn down the power, maybe put a little tiny pinhole through just to collect a few photons, and you can do that. So if you do that, you can get down to the average of a single photon at any one time in a given time window. The problem is, though, is that sometimes you get one photon, but sometimes you get no photon at all, and sometimes you get two. And if you've got two, that means that Eve might make an attack on you and detect your photons undetected. So to do this, you really need to make the probability of having even one photon very, very low, less than 5% chance of a photon. And so that means that the rate of photons you're producing is very, very low, and it becomes impractical. There are better ways of doing it using atoms. So if you kind of remember some chemistry, you've got your nucleus and then you've got your shells for the electrons, if you remember. And the electrons sit around the lowest shell. It turns out if you kind of send in a pulse of light, you can take one of those electrons and push it up to the next shell. Now, if you do that, then you just wait, and that electron will just jump down by itself to the lowest shell that it can because it wants to get into its lowest energy state. And that will produce a photon to get rid of the excess energy. Okay? It won't produce two photons, though, because there was only one electron. So this is a way of guaranteeing that you only get one photon coming out. And if you want another one, then you just send in another pulse of light, and out comes another single photon. So this is what I do, okay? But I don't use real atoms. And the reason I don't use real atoms is because those atoms are kind of small, and they only produce about 1 million photons per second. Now, that might sound like quite a lot to you, but you've got to bear in mind that most internet traffic is, sending bits at about about a gigabit per second, so a billion per second, so 1,000 times more. So what I do is I make artificial atoms, and I make artificial atoms using a semiconductor technology. So semiconductors are the kind of a hard, sort of usually grey material, and they're used extensively in things like microchips for your laptop and things. Now, I use a specialist type of semiconductor to do this, and it's in fact one type of semiconductor encapsulated in another. That semiconductor, that artificial atom, is only about 20 nanometers in size. 20 nanometers is a 20 billionths of a meter. It's really, really, really small. So small, in fact, that in this picture you could just about make out, you see some lines? Those are lines of individual atoms, okay? Now, what is special about this semiconductor is I can get the electrons hanging around the atoms there in that bright white space to act almost like a superatom. All the waves of that electron, they all act in sync. A little bit like that cloud of atoms in that gravimeter, okay? And because there's lots of them, but they all act like one big atom, they emit faster. And so I can get now easily, a billion photons per second rather than a million, so it's much better. The other advantage of this kind of system is that I can sort of piggyback on a hugely important mature semiconductor technology. Semiconductor technology and how you make them is really, really well established because it's really ubiquitous. Okay, this is a picture here of a kind of a light waveguide for my artificial atom. So inside this 20 nanometer atom, I put this inside the little kind of vertical pipe here. It's pretty much doing the same thing as this thing here. It's guiding the light to where I want out of the top. Okay. The advantage of this is that this is really small, and it means I can make lots of them. And I can make them, using quite easily using standard semiconductor fabrication technology. So this is one of, you can see those little tiny marks there. Each of those is a micropillar, as I call them. And there's about 11,000 on here. Okay, this is a research grade thing. The chip will be about 5 mil, and there's about 11,000 on there. That's not very many, actually, but it's enough to keep me going for a while, because we have to measure them one by one, actually. Actually, it's the same kind of technology that we make commercial, what are called microlasers. So this is a picture of some microlasers. Microlasers are basically like my single photon sources, but they emit much more bright light, a bit like this laser pointer here. But they're really tiny, so they're, a thousandth of a millimeter. The point about this is that these are kind of fabricated in their millions. So this is a zoom in of an area of This is called a semiconductor wafer. This is a sort of a dinner plate sized, okay? So on this, there are 100 million lasers. So it's quite expensive to make one of these dinner plate sized wafers, but you just chop it up and then you've got 100 million lasers. And that makes the price of every single one less than a penny. Now that's a really important thing to do, because if we want to make this technology of quantum technology ubiquitous, the actual price of each individual element needs to be really, really cheap. So we have to kind of use technology that's already available to do that. We've still got a long way to go, actually, with our artificial atoms. The major problem is they need to be cooled down with liquid helium to make them cold, to make sure they behave like artificial atoms. So shrinking down the cryogenic technology to do this is, a challenge that we're working on. But actually, that kind of technology is getting smaller and smaller as well. So in this talk, we've kind of gone from the very kind of big, the cities, to the very, very small individual electrons trapped in corrals of atoms. We're looking at going all from quantum particles to cities, okay? But this is really about how quantum technology could help this vision of a smart city, okay? So smart cities, I think, are really important. We're already generating lots of data. It's already being used. Using it well is really important. So the kind of technologies that we can contribute to are things like making an autonomous vehicle system in a city. So autonomous vehicles are, could be a really important part of our future. The advantages you get is that they're much more energy efficient. They are safer. They'll have less accidents, and actually they'll free up a lot of space. So when you're moving around an autonomous vehicle and you get dropped off, it's not going to go and park somewhere. It's going to go and pick up its next customer. So you need many, many less parking spaces in the city. Now, if you were to take away all the parking space in London, you would have about 10 Hyde Parks worth of space to regreen and actually make into a more pleasant city. So this really could be quite, life-changing, for a city. Could be making our cities much more livable. And it's also a great technology because it allows people who are not mobile to use and not able to drive to get around the city as well. We've also seen that quantum technologies can help with big underground mapping programs. There are programs now UK-wide to map the entirety of underground. What these quantum gravimeters will do, and there are other quantum sensors as well, they'll be able to allow us to map more sensitively and further underground than other technologies. And really, that's going to save us a huge amount of energy. It'll actually cost. So it's a huge amount of disruption to sort of dig holes just to find out what something is. It's also, not very green. So construction is a huge contribution to greenhouse gases. And then we looked about security in our cities, both our personal security and security of critical infrastructure. So the quantum technologies that I showed you, looking at sending absolutely secure signals using single photons, that will probably be first deployed in secure critical infrastructure, because it's most important that we actually ensure that these critical infrastructure technologies are secured against cyber attacks. We have good cyber security systems at the moment, but this will really add an extra layer, which is going to ensure that future attacks are not going to be possible. And finally, I think there is real potential in sharing personal data anonymously, but we need secure systems to do that. So this map I'm showing you here with these red dots, this is not a modern map. This is actually the incidence of cholera outbreak in an area of London in 1854. And this is the map that John Snow used. I don't know if you've heard of him. What he did was he showed that cholera is a waterborne disease. He showed that all the cholera instances were coming from a single water pipe in the city. He took off the head of the water pipe, the cholera outbreak stopped, and he proved that cholera is a waterborne disease. Now, I would say that actually this use of health data over a small region of a city hasn't really moved on very much since 1854. I think it's got a huge potential, but really could be exploited more. So I think in conclusion, smart cities are really exciting. We should embrace them, but we should be, We should encourage city planners to incorporate new technologies into infrastructure and plan for the future, but also be very vocal about what we want from these smart cities and make them for us as well. With that, I'd like to thank you all for your attention.